Guess what's happening on Wednesday? Pre-test. That means that I can give you any question out of the back of the book from chapters 1 through 6. Fair game. Okay, we've gone over just the teensy-weensy parts of all that, but my understanding is that's all stuff you should have learned before you even got here. So, adding together capacitors, resistors, op-amps, voltage dividers, voltage dividers, you know, the good, the bad, and the ugly. Okay? I'm pretty lazy, so there's a pretty good chance that that at least 2 of 4 problems will be directly out of the book. Is that true? Yes. Yeah, that might be true. Okay. And for this time around, we're going to make it closed book. But for your other 2 exams, like your real exams, they'll be open book and open note. I just don't care. Not that I don't care. Actually, let me rephrase it. I do care. You know, you ought to have stuff memorized, but at the same token, you know, I think it's okay to go through your notes. And I'm not trying to test your memorization skills. I'm trying to test your understanding. And people who have taken my test will tell you that it doesn't really help much, even when it's open note. So, any questions about Wednesday? Hard to say. I'm guessing like 4-ish, but you know, they might have multiple parts. And I won't be here to give the test. Elliot will be giving the test. So once again. But you still got to come, right? Even though I'm not here.
So this pre-test, this means it's been graded?
The question was, will the pretest be graded?
Yes. If you go to your syllabus, which was handed out on the first day of class, if you go to the handout that I posted on Blackboard for everybody to read, but which nobody did, you will see that the pre-exam is worth 10% of your grade. Okay? That should be 10%. That's like 10 free points, right? You already know this stuff. You already took the prereq. You already know how to work a resistor. Come and collect 10%, right? I can't make it any easier than that. Yeah, so 10%. What's that? Index card with formulas? What formula are you going to write down? Fine. If you want to have a piece of paper, like one piece of paper with like handwritten stuff on it, then that's fine. Whatever. It's not going to help. So 1 8.5 by 11, front and back, handwritten. There you go. What else do you want? I mean, answer key. Yeah, well, good luck with that. Coffee. Okay, all right. Let's keep talking about RC circuits because we need to make friends with them. Okay? So here's where we were on Friday. We did a little bit of this, a little bit of this, and a little bit of this. Okay? We got a voltage source, a resistor, capacitor. We have an output voltage that we're going to take at the top of the cap. And we said, holy cow, we need a way of describing this circuit. And what we did is we equated the current going through the resistor to the current going through the capacitor. And after some math, we came up with this expression, which was that the derivative of the output voltage plus the output voltage divided by RC was equal to the input voltage divided by RC. And we said, hey, that is a first order differential equation. And then I said, y'all took differential equations, right? And you guys said, yeah! And then I said, how do you solve this? And you said, And that was basically Friday. So, after some prodding, some of you woke up and remembered that when you solve a differential equation, you solve it in 2 steps. The first step is to get the homogeneous solution. And you get the homogeneous solution by setting the input voltage to 0. That's the driving signal. Okay. So to get the homogeneous solution, you set your input to 0 and you solve. And in that case, we discovered that the output voltage, and actually once we did that, it was easy, right? Then it was just a separable differential equation. We got V out, dV out over V out equals minus dt over RC. We integrated both sides, and we got K e to the minus t over RC. All right? Now we have to get the particular solution. Anybody remember how to get the particular solution? I always love this. Not the initial values. But there's like a whole other formula that we need to get before we even get to initial values. You guess. I'm serious. You guess, and then you verify that your guess was correct. Here's what I mean by that. So for this problem, what we're going to do is we're going to apply a step input. So that means that V in is going to look like, it's going to start out as a voltage of 0, and then at t equals 0, I'm going to flip the power on, and let's say we up that, the power comes on to 1 volt. All right? So, for positive time, I can think of my input voltage as a constant. Can we agree with that? And if you were to look at the step voltage, for positive time, my input is a constant. Okay, so input is constant. So, I'm just going to guess. I'm going to guess that my particular solution is also going to be a constant. How do I know? I don't know. What does it say? It says guess. So I'm just going to guess that because my input is a constant, I'm going to guess that my output voltage is also a constant. Now, so I'm done with the guess part. Okay, I'm just also going to guess that it's a constant. Now, how can I know if I'm right? Well, the way that I know that I'm right is I substitute into my differential equation, and I see whether or not I can make my equation work with my input being, with my output voltage being a constant, as per my guess. You with me? So let's guess. What do you want to call the constant for V out? Let's guess that V out is some constant. What do you want to call it? We can't use C, because C is the capacitor. I don't want to use K, because we already used K over here. So I need another name for a constant. B. Okay. Some constant. So let's see if we can make our differential equation work subject to the guess that our output voltage is a constant. All right, let's go and inspect our differential equation. Okay, if V out is B, what is dV out dt? What is the derivative of my constant V out? Right. If V out is the constant, then its derivative had better be 0. That's nice. Plus V out over RC. Well, what is V out? It's just a constant. B. And that has to equal my input voltage over RC. So what is my input voltage for positive time? I actually have a number there now, right? It's the constant 1. So, let's solve that for one more step. B equals 1. So here's what this tells me. Is it possible that my output voltage is a constant? Absolutely. It is possible as long as that constant equals 1. If it's any other constant, it won't work. But I've just proven that my particular solution is the constant 1. Okay, because it wasn't, I guessed that it was a constant. I checked to see if that guess made any sense. And in fact, I got something that did make sense, right? I said, this will totally work as long as I just make sure that my constant equals 1. So, in summary, is it possible that V out is a constant? Yes, it is, as long as that constant is 1. Or whatever, the same voltage that V in equaled. So let's put it all together. My output voltage is equal to the sum of the homogeneous solution, which is that thing I just erased? Awesome. So it's equal to the homogeneous solution, which was K e to the minus T over RC, plus the particular solution, which was 1. And I'm almost done. What's the last thing I need to do? Yeah, I want to get rid of the K, right? K is not okay with me. How am I going to get rid of K? Somebody said it before. It was just the wrong time to say it. Initial values. Okay? To get rid of K, I need to figure out my initial value. Okay, so what do you think my output voltage is at time t equals 0? Okay, so starting at time negative infinity, my input voltage is 0. Okay, so if my input voltage is 0, what's the output voltage going to be? If this is 0, any guesses? It means 0, right? If there's any charge on that capacitor, it all would just drain out through the resistor and there'd be 0. So we can all agree, I think, that if your input voltage was 0, your output voltage coming into time t equals 0 would also be 0. And that is our initial, that's our initial value. Okay, well let's substitute. So we'll substitute in V out equals 0 and t equals 0 in this equation. And we should have everything we need to solve for K. Is that correct? So if I take this equation, it should be 0 equals K e to the minus 0 over RC plus 1. Okay, any takers on e to the 0? E to the 0 is always 1. So this is a 1. So 0 equals K plus 1. Therefore, K equals negative 1. There we go. And we put it all together. And we get your final answer for the step response. V out is a function of time equals 1, which is your particular solution, minus 1 e to the minus t over RC. And we put a box around it. And we're going to spend the next half an hour talking about that equation, and what it is and why it matters, and a whole bunch of other stuff. Okay, first question. What is the units of R times C? Seconds per milliliter? 1 over seconds. So first question, what is the unit I'm hearing seconds. How can I change it from seconds to seconds? How do I do that? How can I be sure?
Say it.
What's that? Just say it? Seriously, how can I know for sure? I can think of 2 ways I can know. That's the hard way, and we're going to do that in a second. What's the easy way? You're right, but I want the easy way first. Look at e to the stuff. Okay? Whenever you take e to the stuff always has to be dimensionless. It's like log, right? It just works that way, right? You can only exponentiate a number. You can't exponentiate like a unit. You can't take e to the 4 pounds or e to the 3 seconds. You can only take e to the 3, where 3 is just some unitless number. Okay, so if I want to take e to the some unitless number, and I've got seconds in the numerator, what do I have to have in the denominator? Seconds. Now, dimensional analysis. Can I prove the same thing with dimensional analysis?
Yes.
Thank you. Okay, we got 2 equations, right? We know Ohm's law, which says volts V equals IR, right? So I would say, actually, okay. So we'll say volts equals amps times ohms, right? That's Ohm's law. And then the capacitor equation is I equals C dV dt. So that is I in units of amperes equals capacitance in units of farads. I equals C dV dt. What's the units of dV dt? Volts per second, right? Now I want to know if what do I get if I multiply resistance, which is in ohms, times capacitance, which is in farads. So couldn't I just take this, solve it for ohms, this, solve it for farads, multiply them together and see what happens? Yes, I could. Okay. So if I solve this for ohms, I find out that ohms equals volts per ampere. And if I take this and solve it for farads, I found out that a farad is equal to an amp second per volt. And if I multiply ohms times farads, ooh, look what happens. The amps cancel, the volts cancels, and I'm left with seconds. Seconds. So resistance times capacitance is always seconds. Commit to memory. Fun. Okay, what is this going to look like? So let me just draw this a little bit bigger so we can focus on it a little more. I think I'm going to draw it right here in the middle. Okay, so here's my input voltage. I'm going to try to draw this as cleanly as I can. So here is my input voltage. For my output voltage, we said it started at 0. We said it was 0, right? That was our initial condition. So now I'm going to hit that point. So help me draw this. What does the plot of 1 minus e to the minus t over RC look like? Let's start with t equals infinity. What happens when t equals infinity? What happens to e to the minus t over RC? All right. If I let t equals infinity, I've got e to the minus infinity. Is it 1 or 0? Let's get an answer.
1, 0.
E to the minus infinity is 0. So 1 minus 0 is 1. So I know if I wait long enough, my output voltage is going to be 1. Because 1 minus 0 is 1. And what about in the interim? How's it going to get to infinity? How's it going to get to 1 volt? Okay. It's going to, so we said when t equals 0, it'll be e to the 0, which is 1. 1 minus 1 is 0. Then if if t is small, then I'll be subtracting off like a relatively small number from 1. And then as t gets bigger, I'll be subtracting a bigger and bigger number off from, I'll be subtracting a smaller and smaller number off from 1. So it's actually going to wind up looking like that. That is the plot of V out of t. Okay. So what you're looking at is the step response of a first order system. Anytime you have a resistor and a capacitor, regardless of what the value of the resistor and the capacitor is, it will always have a step response that looks like that. So let's look at this. Let's start by talking about what this means in terms of the circuit. So initially, the voltage over the cap is 0. And then what starts to happen to the capacitor voltage? Goes up, right? I mean, this is the capacitor voltage, right? Over time, voltage starts building up in the capacitor. Right? It gets bigger and bigger and bigger and bigger. Until finally, what happens? The cap charges all the way. Right? At t equals infinity, this capacitor, according to my diagram, is fully charged up to V equals 1 volt. So what's the current situation at t equals infinity? How much current is flowing through the circuit? At infinity, this voltage is 1. And this voltage is at t equals infinity. Right? Just look at the picture. This voltage is also 1. So how much current is flowing through that resistor? 0, right? There's no voltage drop, so there's no current. So basically what happens is, in the beginning, there's a lot of current. Okay? And as this current, as this movement of charge, guess where that charge winds up? It collects in the capacitor. And as charge collects in the capacitor, its voltage goes up, because that's what capacitors do, right? Q equals CV. So you start depositing charge on the capacitor, and the capacitor voltage gets bigger and bigger and bigger and bigger, until finally the capacitor voltage reaches the same value as the input voltage. And then nothing. Then it's just that you can't put any more voltage across it than that. So it turns the current starts to tail off, and then it's full. So basically the capacitors. So here the capacitor starts empty, and here the capacitor is full. So here's a question. Suppose I wanted to fill the capacitor faster. I reckon there's 2 ways I could do that. Right? Suppose I wanted to fill the capacitor faster. What's one way I could do that? Can't take away the resistor. There's a resistor in that circuit.
Lower the voltage.
Without lowering the voltage. Basically, how can I mess with R and C? Okay, so if I want to fill the cap faster, one option is I could lower the resistance. Why? How's it? Give me a feel. Like what's that? Why would? Yeah. So lowering lowering resistance, we learned last week, always increases current, does it not? So if I lower R, I increase current. If I increase current, because remember, current is charge per unit time. So if I increase my current, then in the same unit of time, I'm depositing more charge on my cap. So my cap is going to charge up more quickly because I'm making it easier to put more charge on there. So absolutely. Lowering the resistance, so let me follow the chain of events. Lowering resistance means increased current, which means increased charge on the capacitor, which means the voltage goes up faster. Absolutely. What's the other way I could fill up the cap faster? We're done with R. What could I do to the capacitance to make it fill faster? I can't. I just want to change the capacitor value. If I want to fill the capacitance, if I want to fill the capacitor bigger, shall I make it bigger or smaller? Smaller. Right? You know, if I give you a bucket that's this big, and I say fill it with water, right? You're going to wait a long time for it to fill. Or you can make a little itty bitty bucket. Okay? You fill it up right away. Okay? So, the other option you have is smaller capacitor. Okay? If you have a smaller capacitor, then you need less charge to fill. And because you need less charge, it'll take less time to fill. So that's kind of cool, right? If you want to fill your capacitor faster, right? I mean, if my goal was to, let's say, instead of filling the cap like this, I wanted to fill the cap like that, I could either decrease my resistance or decrease my capacitance. That's kind of interesting. Let's come back and look at this equation. Look at R and C. They're always together, right? And we said R and C is in units of time. So watch what I'm going to do. I can simply take the product RC, and it's so common, I'm going to replace it with this little Greek letter called tau. Anybody ever heard of tau? It's the time constant. It's the time constant for this circuit. And it's simply a shortcut for saying RC. So, why am I telling you that? Look at this conversation we've just had. If I want to have the amount of time it takes for me to charge this capacitor, I can either half the resistance or half the capacitance. But in both cases, what have I done to the time constant? If I half the resistor, what do I do to the time constant? I half it. If I half the capacitor, what do I do to the time constant? I half it, right? If I half R, I half tau. And if I half C, I half tau. So, in other words, what I said over here, if my goal was to fill the capacitor faster, I could either lower the resistance or lower the capacitance. But really all I've done is lower my time constant. I like that, right? Here's why I like this. I like this because intuitively, we could come to an answer on what to do with the resistor and the capacitor just based on what I would like to think is intuition, right? You either have lower resistor, means more current, or you have a smaller capacitor, which means you need less charge to fill, okay? But mathematically, the equations actually match my intuition. Mathematically, what the equation says is, look, your time constant is equal to R times C. Okay, if you lower your time constant, doesn't matter how you got there. You could either lower a resistor or you lower a capacitor, or lower both of them, right? Either way, as long as you lower your time constant, it's going to take more time to charge the capacitor. It's going to take, less time to charge the capacitor. So there's this concept that it's not really the value of the resistor that matters, and it's not really the value of the capacitor that matters. It's their product, right? It doesn't matter how you get to your time constant. Well, as long as if you make the time constant smaller, the capacitor charges up faster. What do you think? Questions? Does it all make sense? I'm that good? Sweet. All right. Well, make sure you put that in your course evaluations at the end of the semester. I'll get a nice raise. Okay. How long does it take to charge the capacitor? 4 seconds? How do you know what the time constant is? 4 seconds? I'm not buying it. What if your time constant was an hour? What's that? Yeah, but you can make really big capacitors. Does anybody have a really big capacitor in their car? Does anybody have one of those crazy woofers that makes the street shake? There's always somebody that has one of those. Right, if you've got a crazy car stereo, with the all aftermarket, custom, whatever, thousands of dollars jobby, right, you can't run that off your car battery directly because you'll blow up your car. So one of the things they do when they put in those sound systems, I only learned this because a student told me a couple years ago. The first thing you do is they put a big old capacitor, okay, you want to learn some real circuitry? Here you go. Here's your got battery. Okay, your car battery can only supply a certain amount of current at a time. So what we're going to do is we're going to basically, got to put a little resistance there, but you put a big old capacitor in series with it. Okay, so what's going to happen to that capacitor very quickly? It's going to charge up. It's got lots of charge sitting on it now, right? Now, you put your big old car stereo in series with it. Now, car stereo, like any stereo, takes a lot of current to drive those big woofers, right? To make the street shake. Okay? That's a lot of current. Boom, 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 right? That's amperes of current. Where's all that current going to come from? You're going to suck that out of your battery? Your battery can only supply so much current at once. So what you do is, you put a capacitor there, let the capacitor fill up, and once it's filled, it can supply that jolt of current that you need. Okay? If this car stereo says, I need this instantaneous jolt of power, it sucks it right off the capacitor. Okay? And then the battery can recharge the capacitor a bit more slowly, which it can do. It's just the battery has a limit to how fast it can actually deliver that power. So you transfer the power into the capacitor, and the capacitor can quickly drive the speakers on a millisecond range, and then the battery can kind of take its time filling up the cap. But I'm told that in car stereos, this could be like a farad, right? It'd be like the size of a trash can. Okay, sitting to actually make this system work. Yes.
Do we need anything else like fuse or op amps?
Yeah, I mean, there's there's a giant. You actually have the electronics in the middle. You don't just wire a capacitor to a. No, I'm serious. You've got an amp. You're going to have an amp with that takes lots. The amp is what's actually sucking the power off the cap, right? Well, no, actually, that's not true. The speakers actually need power to be driven as well. So, there's a whole lot of electronics in there. But, conceptually speaking, that's how it works. Actually, that's not true. I wired a car stereo once, but it wasn't this fancy. It was just like a new faceplate. Anyway, but yeah, so you can get big capacitors that take 4 hours. So yeah, back to your question. So I've got a capacitor, I've got a circuit with a time constant of an hour. You still going to stand by your 4 seconds claim?
Actually, I remember what I was actually thinking of. The four time constants, what they say.
Ah, okay, now we're getting somewhere. All right, so let's say, for the sake of argument, that my time constant is, let's pick a number. 0.6 watts. Okay, always somebody got to pick a non-round number. Fine. 0.6 seconds. Okay, fine. Whatever. Okay, so let's say this is the curve. Let's say that curve corresponds to tau equals 0.6. Okay? So let's see what happens. Did any of you bring calculators to your engineering class? No, that's okay. I brought one. That's fine. It's okay. Don't feel like you have to get yours out. I got it. Okay, so what I'm going to do is I'm going to plug different numbers into this equation and see what comes out. All right? So I'm going to start by plugging in 0.6 for t. Okay, for this series of equations we're going to do, we're always going to assume the time constant is 0.6 because that's what you said. Okay, we've built a circuit with a time constant of 0.6. So let's see, how much will this voltage have charged after one time constant when t is equal to 0.6? So in order to do that, I'm going to substitute in t equals 0.6, tau equals 0.6, so it'll be e to the minus 1, so 1 minus e to the minus 1. That's not right. Let's try that again. All right, I got an answer. Does anybody else have an answer? 0.6. 0.63, but whatever. Okay. So let's see. Is that a half? Seriously, is that a half? Okay, but it's 0.5. 0.6. No. What the hell did I do? It's half. That's half again. Yeah, okay. 0.6, 0.7, 0.8, 0.9. Good enough, okay? So let's see. 0.5, 6, 7, 8, 9, and 1. Okay, so here's 0.6. Oh, dear. So this was after one time constant, okay? So I waited for 0.6 of a second, which was one time constant, and my voltage got roughly 60% of the way to its final value. So clearly I've got to wait more than one time constant for it to charge. Let's wait for another time constant, okay? So let's repeat this calculation. We're still going to keep our time constant at 0.6, but now instead of waiting for 0.6 seconds, we're going to wait for two time constants. Okay, so we're going to let t equals 1.2. So e to the minus 1.2 over 0.6 is e to the minus 2. 1 minus e to the minus 2. So you do it and I'll do it and we'll see who's right. All right, what you get? 0.86? I'm getting about the same thing. Here's 0.8, here's 0.86. If I had any common decency, this distance and this distance would be the same, right? Because it's one time constant and two time constants. But, you know, if you wanted prettier graphs, you should have gone to Drexel. Oh, that joke never gets old. Okay. All right. So there, we waited two time constants. Okay. So we said, I should probably make a table or something. So waiting for one time constant got me to 0.63. Waiting for two time constants got me to 0.86. Am I up all the way? Not really. Shall I wait another time constant and see how far up I get? Let's wait for, okay, so let's sub in a third time constant. Have you noticed the pattern yet? Does it matter what my time constant is? Look at what I'm doing. I'm doing 1 minus e to the minus t. When I say three time constants, I'm saying three time constants over tau. Does it matter what my time constant is? Nope. That's why when you said 4 seconds, I was like, no, it can't be true. Yeah, I know, you meant, right, exactly. Okay, so we're going to wait for another time constant. Doesn't matter what my time constant is, we'll just wait that much more time. So let's wait for a third one. Oh, we're getting closer now. Any takers on this one?
0.95.
Oh, you getting 0.95? Oh, yeah, that's what I got. Okay. So I wait for 3 time constants. Now I'm getting somewhere. Now I'm all the way up at 0.95. And if we wait for 4 time constants, .98. And if I wait for a 5th time constant, .99. Isn't that kind of cool? So at the beginning, when my time constant was 0, I was at 0 volts. So in the first time constant, I went up by 0.63. That's a lot, right? I did pretty well. In the next time constant, I only went up by 0.3. I went up by about half as much. And then I went up by about 0.1. And then I went up by, so each time constant gets me less and less, right? So then I only went up by 0.03. And then I only went up by 0.01 in that same stretch of time. So each time constant gets me closer, but it's like a diminishing returns. Less and less for each time constant. Mathematically speaking, how many time constants do I have to wait to get to exactly 1 volt? Infinity. Am I really going to wait infinity? Probably not. Okay, we got things to do. We can't wait that long. Reasonable people differ. I was always taught when I was in school, I was always taught that 5 time constants, like once you wait 5 time constants, you know it's charged up all the way. But I mean, if you've learned 4, I mean, it's not like it only differs by 1%. It's not like we're going to split hairs over that. So you wait like 4 or 5 time constants, it's pretty much charged up all the way, regardless of what the time constant is. Right? Regardless of what the time constant is. Pretty neat. Okay, so now, if I decrease my time constant from 0.6 to some other number, 0.1, think about how this is going to change. If I decrease my time constant, so we just said that after 1 time constant, it always goes up to 0.63. Does it matter what the time constant is? No. So if I half my time constant, what's going to happen? I'll get to 0.63 half as quick. Right? Now, instead of 1 time constant taking 0.6 of a second, 1 time constant will take me 0.3 of a second. And that will still get me 63% of the way there. I will have just gotten 63% of the way there twice as fast. And that makes sense, isn't it? Look at it. We already agreed that our time constant, a smaller time constant, should mean it rises faster. All right, same thing. We know 2 time constants is going to get us 86% of the way there. All right, now instead of 86% of the way there taking 0.6 plus 0.6, now it'll take us still 2 time constants, but they're half as big, 0.3 plus 0.3. So roughly like to right there. Okay. So making the time constant smaller, so this is smaller time constant. And if I were to draw a curve for you like this, that would indicate a larger time constant. Crazy. Anybody have like an old-fashioned, are they really that old-fashioned? Anybody have a camera with a flash on it? And like you turn on the flash and you hear that little boop, and then it like takes a second before the light comes on and you're ready to take the flash. What do you think's happening? Yeah, your flash has got a little capacitor sitting behind it, right? You've got to take a whole bunch of charge out of the battery, charge up the camera, charge up the flash, and then when you take the picture, all of the charge that's on the cap instantly drives out through the light. Okay, that's get a large flash. Okay, but that noise you hear as the flash is charging, right? It's a time constant. You're charging the cap. Okay? So, I'm guessing that if you want a certain amount of charge, you need to have a fixed capacitor size. Okay, let me erase this for a second. Actually, let's stick with the example of taking a picture. Okay, so I'm just going to draw the same picture again. So here's the capacitor that works your flash. Okay, so we charged it up, and the voltage here charged up, and it looked something like what we've just been talking about, where the amount of time it took to charge depended on the time constant. Okay, nothing more, nothing less. Now I've got a switch here. Okay, that's a light, believe it or not. There's your flash. Okay. So what I'm going to do is, at the instant I take the picture, okay, pardon my lousy drawing. It's not my strong suit, which is really a weakness in this line of work. All right. So what I'm going to do is now I'm going to take the picture. So at the instant I depress the shutter, this switch is going to open. Okay. So I'm basically going to take the capacitor. I'm going to take the battery out of the circuit. And instead, I'm going to close that switch. So all the voltage, all the charge that's sitting on my cap is going to do what now? Right. All those little charges that have been stored up on my cap, they're instantly going to tank out through the flash, hopefully very quickly. All right. So if this is the voltage on the capacitor, here it was charging. Now, once I take the picture, what's going to happen? What's that voltage going to look like? Absolutely. It's going to come back down. And we know that if you wait long enough, you'll take all the charge off that cap, and that voltage will go back to 0. Okay. How do I know it's going to be a first-order dynamics? Do I know it's going to be first-order dynamics? Right. You've got one resistor, you got one capacitor. Done. First order dynamics. Okay? If you have two capacitors, you have an inductor and a capacitor, then it's a different story. Okay? But if you've just got a resistor and a capacitor, you've got first order dynamics. It's exactly the same story. The only thing that's different is whereas before the initial voltage was 0 and the final voltage was 1, now it's the other way around. The initial voltage is 1 and the final voltage is 0, but it's still going to follow first order dynamics. What's the other thing that might be different in this case on the discharge cycle? Has the capacitance changed? No. Has the resistance changed? Yeah. We're not using this resistor anymore, are we? Right? This was the charge resistor. What about when I discharge? Is there a resistance? There's a little resistance inside that light bulb, right? That resistance, that light bulb's got a little bit of resistance to it. Do you reckon it's a real big resistance or a real small resistance? Real small, right? Because when you charge up your battery, when you charge up your flash, it goes boop. It takes a couple seconds to charge. Does it take a couple seconds to discharge? Do you see your flash go like bleh? Like no. It comes out like a millisecond, right? Everybody squints. So this is probably going to be a really small resistor by design, right? You want all that charge you've gotten to dissipate as quickly as possible. So you want this to be a really small resistor. So whereas you might have had one value of tau equals RC for the charge phase, for the discharge phase, let me make this a little more obvious, you may have had a very different value of RC, right? If your resistor was really small, then your time constant is small, and it'll discharge very quickly. But it's still first-order dynamics, right? How long will it take to discharge 63% of your voltage? One time constant. How long did it take to charge 63%? One time constant. How long did it take to discharge 63%? One time constant. The only thing that's different is your one time constant here is probably going to be a whole lot smaller than it was on the charge side, but it's still one time constant. Okay? So always, always, always. We're going to practice this again on Friday when we come back. Okay? But these are kind of like the rules of the universe with these first order things. One time constant gets you 63% of the way there. Two time constants, 86% of the way there. So on and so forth. Charge, discharge. That's it. Okay.